Hi everybody. Today we're going to be talking about the use of combinations. Now before we were talking about permutations, and if you remember from that lesson, permutations, the order matters. If I had Alan, Brittany, and Greg, and I had asked you before how many different ways could you order them, and order matters, you could have had Alan, Brittany, Greg, Alan, Greg, Brittany. You could have had Brittany, Alan, Greg, Brittany, Greg, and Alan. And then you could have had Greg first, Alan second, Brittany third, or Greg, Brittany, Alan. Order matters, permutations, there were 6 answers. However, today what we're going to be looking at is how order does not matter. And if order doesn't matter, Brittany, Alan, and Greg is the same thing as Greg, Brittany, and Alan. Whereas last time we were talking, this was mp4. Today, when order does not matter, we're going to learn a new formula. Now, some things to look at. Permutation versus combination. Examples, it can be very confusing, so here are a few of those examples. A permutation, remember, permutation, order matchers. Picking a team captain, a pitcher, and a shortstop from a group of people. Or picking your favorite 2 colors in order from a color brochure. Or picking first, second, and third place winners. And we did a couple of these examples before. However, combination where order doesn't matter is a little different. Picking 3 team members to form a group. It doesn't matter who's first, second, or third, you are part of the same group. Or picking 2 colors from the brochure. It doesn't matter if you picked red or blue first, the fact that you picked them both together, that's what matters. Or just picking 3 winners. Just picking the top 3 and not worrying about their order. That's what makes a difference between permutation and a combination. Now I talked about how before we had that formula for permutations, and again, when order matters, we had a formula, NPR, where you chose N topics and you actually picked R of them and the order mattered. And that was N factorial over N minus R factorial. If you look at when the order doesn't matter, and that's what you have with a combination, you have something kind of similar. You have NCR, or some people like to call it N choose R, and you have the same thing that you had before. Actually, I'm going to make that a different color here. I'm going to match that up. It's the same thing, still wrong color. Same thing as our permutation formula, but instead of ending it right there, I also have this extra little feature of timesing by what you are selecting from. So this is our formula for combination of n objects taken r at a time. How do these work? Well, classic examples here are with a standard 52 card deck. Again, if you're not familiar with the playing card deck, that's okay. I wasn't either. And so I started playing with them and I found out that there was 52 different cards. There was the Ace of Spades to the King of Spades, and you had 4 different suits. So if I gave you an example, a standard deck of 52 playing cards has 4 suits with 13 different cards in each suit. 4 times 13 is 52. If the order in which the cards are dealt is not important, you and I are hanging out, we're dealing cards, and you get 5 of them, how many different 5-card hands are possible? Now for those of you who play a lot of cards, you know that certain hands are better than others. I don't care what kind you get. All I want to know is how many different ways could you get 5. So when I set this up, I have 52 cards to choose from. Order doesn't matter, so I'm using the combination formula, and I'm going to select 5 of them. When I set that into my formula, I have 52 factorial over 52 minus 5 factorial times another 5 factorial. Now, I could break this down as 52 factorial over 52 minus 5 is 47 factorials, and then times another 5 factorial. As we were talking from last time with permutations, you can cross off a lot of these 52 factorials with the 47. In fact, what you would be left behind with, and let me just move these down, what you would be left behind with is 52 times 51 times 50 times 49 times 48 in the numerator. In the denominator, however, the 47 factorial divided out, 5 times 4 times 3 times 2 times 1 is left behind, and I could have 2,598,960 different 5-card hands possible from a standard 52-card deck. Now, how many 5-card hands if all 5 cards are the same color? Not the same suit. So my question is now, which color do I pick? Do I pick the black color for the spades and clubs? Or do I pick the red color for the hearts and the diamonds? That is why I have this choice right here. 2 different colors, black or red, and I'm picking one of them. And then 26 numbers or cards are in each one of those suits, whichever color I pick, and then I want 5 of those. So when I type that into my calculator, and if you were typing this into a scientific or a graphing calculator, it's going to look like this. You have the 2, and then you go into your probability section, and it's an NCR and a 1. Sometimes you may want to put a parenthesis around that just to be safe. Times, because you are including the choice of color with your card sides, 26 NCR 5. And when you figure out those numbers in your calculator, this is 2 times 65,780. Get those numbers together. There are 131,560 different 5-card hands that are the same color.